not quantity.
All righty. So we are back into, what is this, about week 5 of the semester, right? Is that what it is?
I think it's
Is it week 6 already? Cool.
We're all on the verge of death.
So almost halfway through, right, is what it is. We're getting there. And we had finished up the equilibrium chapter, and now we're going to take what we learned in that equilibrium chapter and apply it to a couple, let's say, specific, well, how should we say this? We're going to take equilibrium and look at it in 2 very specific applications. The first that we're going to spend quite a bit of time in is just acids and bases, and just how equilibrium affects those. Now, for those of you guys who are paying attention, I guess, or thinking or looking or kind of going, why in the world am I even doing this to begin with, right? If we're going to spend about 2 chapters on acids and bases here in Gen Chem, it's probably a fair statement that acids and bases are pretty darn important in all of chemistry. It's going to be especially true when you get to organic chemistry. Organic chemistry it basically all begins with acid-base chemistry, and then everywhere in biochemistry also, right? There we go. Right? So this is stuff that's going to be over and over and over and over and over and over and over again. Now here's the unfortunate part. I'm going to teach you guys acid-base chemistry here, and by the time you guys get to organic, you're going to have forgotten it, and I'm going to have to teach it to you again, and then you get to biochem, and you're going to have to say, what did I remember in Gen Chem, and you have to learn it all over again. So anyway, the point I'm trying to make is that this is one of the key topics that you guys will see. And as with most of chemistry, it all builds upon itself, right? You know, organic builds on Gen Chem, and biochem builds on organic. And so if you don't have a good foundation there, it's going to be that much harder when you guys get to these other courses, is all I'm trying to say with that. Yeah, what's up?
So are we going to get to dump baking soda and vinegar?
No. You talking about in the lab?
Or anywhere, really.
I'm not stopping you from what you do at home, right? You know, if that's what you want to do, go for it, right? But, so anyway, we're going to spend a little bit of time here, and most of the things that we're going to talk about relate to the equilibrium chapter, right? So if you're not comfortable with equilibrium yet, then, well, you got to get that way, right? Because basically the next, all the way through chapter 17 is all going to be calculating K and using K and doing all these things, right? So essentially all the next exam is going to be a bunch of capital K's, right? And then just kind of the specific calculations and ideas and concepts that come from that. But where we're going to begin is just kind of talk a little bit about what is an acid, what is a base, and some of the different definitions and ideas and concepts that come from that. Now, having just given my, 5-minute spiel here about all this stuff, this is where the concepts come from, right? What is an acid, what is a base? Because before you do acid-base equilibrium, guess what you have to know? 2 things. What's an acid and a base, and what's equilibrium? Got it? So we talked about the equilibrium part, and now we need to figure out what in the world an acid and base is. So one of the challenges, and I'm going to tell you guys to memorize something here in a little bit, right, is just to be able to identify what acids and bases are, right? And unfortunately, or fortunately, depending on your perspective on these things, we don't spend too much time with that in this class. I wish things were kind of structured differently, to be honest. It'd be far more important for you guys to be able to identify conceptually what are strong acids and bases here, and then we can worry about the pointless equilibrium calculations when you get to biochem, right? Do you know why I say that? Because I don't have to teach biochem, right? and these calculations tend to be pretty complex, right? However, as with all the calculations in here, right, the big secret is just doing what? Getting comfortable with running the calculations, right? It's just a bunch of K's. Now, we're going to learn the new K's, right? We're going to learn what Ka is, and Kw, and pKa, and pKb, and Kb, and all these kind of things, but guess what they all are? K's. And guess what they're all based on? Equilibrium. Got it? Right? So if you don't understand that equilibrium part of it, then all this other kind of stuff is going to just kind of quickly snowball into something that seems unmanageable. Okay? yeah, so I think that's kind of what I just wanted to say for my intro spiel for you guys for this stuff. So I think, aside from that, then we'll, as usual, we'll get started with some prayer, and then we'll start to figure a little bit out about acids and bases here. But Lord, we just thank you. We just thank you for another week and another gift. Lord, we just pray that we learn how to humble ourselves today, Lord, and just learn a little bit about what it is to mean for you to be our Lord. And just, it's easy for us to say these things, and we call you this very naturally. But, Lord, we just have to understand, where it is and what our relationship is with you. Lord, we thank you that we can talk with you whenever we want. But you also do give us commands, and you expect us to obey them in the best that we can, Lord. And we just pray for your strength and courage, just to fill us today so that we can carry out those commands. Help us to be good and faithful servants, and just understand the relationship that we have with you and with those around us, Lord. We just pray all this in your name. Amen. All right. So, acids and bases. One of my favorite things to talk about in OChem. And so we'll do a little bit of the conceptual stuff here today. So I think at this point in your life, and having made it this far, whenever I say the term acid and base, you guys immediately already have something in mind, right? Your universe already contains a definition for what acids and bases are, right? As Rachel asked earlier about this, building the volcano there, right? I'm sure at some point in your life you guys made the little red food dye volcano at home, right? You made the little paper mache mountain, and poured some baking soda in there, and added some food coloring, and dropped in some vinegar, right? Wasn't life easy back then? Now you're gonna have to calculate that stupid volcano. Oh gosh. It's gonna be terrible, just terrible. But anyway, right? But in reality, kind of just a little bit of a historic context that, I don't know if I would say I was thinking about this, but I reflect upon it at least, is that, as we've got these very good definitions of what acids and bases are today. It wasn't really all that long ago where we didn't really understand what acids and bases were, right? And one of the initial definitions came from Arrhenius there, where what he noticed was, any substance which ionizes in water to produce protons, he defined that as an acid, and anything that produces hydroxide is a base. And that's not a bad definition, and that's kind of, I think, what everyone thinks about. And usually that's kind of what we mean when we discuss acids and bases. However, what we should be saying is something that produces hydronium, right? And something that produces hydroxide, right? And so, because when we say the word proton, we've got something in mind, right? Proton is one of these fundamental building blocks, right? It's the three pieces that go together to make a atom, right? A proton, neutrons, and electrons, right? So why in the world do we call these things protons? Now we're going to see this, and you're probably going to hear me use this quite a bit, this term proton, as we go around, just because it is the common term, and it is accepted kind of for what it is. So what in the world is a proton? Well, when we talk about protons in the, I can write, okay. And when we talk about protons in the acid-base sense, what we're talking about is an H, a hydrogen, with a positive charge. Got it? So question, why in the world do we call those a proton?
That's what they are.
What do you mean?
One proton.
What do you mean?
Hydrogen.
How do I build a hydrogen atom? One proton and
A neutron.
one electron. If I take away an electron to make a plus, what do I make? I just have my nucleus there, right? Just my proton. Got it? Now, is free H plus just floating around in solution? No. Right? So remember, it's always going to be associating with water or something else that's around it, right? You just can't have charges just that aren't balanced in some way, right? There's always a negative where there's a positive, and all these kind of ideas that we talked about as we've gone through chemistry so far, right? But when we're talking about proton, we're talking about H plus, right? Now, if I take H plus and I add H2O, what do I make? H3O plus, right? So this hydronium right here, which in some of the polyatomic ion tables there, right? Some of the polyatomic ion tables have hydronium listed there because it's common, it's good to know the term and memorize it and all these kind of things, right? So H plus, H3O plus are in many ways interchangeable, right? So when we talk about a proton, we're just talking about those species, is what it is, okay? Hydroxide may be a little bit simpler to understand. This is one of these polyatomics that we've talked about and discussed and all these kind of things, right? So there's that. So question then, why is something like ammonia considered basic, right? Because if we put ammonia into water, right, it's not going to dissociate into H plus and then NH2, right? Well, how in the world do you guys know that? How do you know that ammonia is not going to dissociate when you put it into water? Yeah?
Because it's covalent?
Exactly, right? It's a covalent molecule, right? Nitrogen is a non-metal and hydrogen is a non-metal, and when you put covalent species in the water, they're not going to break apart. What will break apart? Ionic compounds, right? So same ideas, right? We're just building off this stuff that we talked about previously. So we're going to talk a little bit about why ammonia is basic and some of these other ideas that come out of this, right?
Does it react to the oxygen in the air?
Will ammonia react with oxygen in air? Sure, but we're talking about putting it in water, though, right? So after Arrhenius kind of came through and did all his important work, not just in acids and bases, right? We've already talked about Arrhenius equations and all these other things, very, very important scientists. But Bronsted and Lowry came by, and we typically just call this the Bronsted definition of acids and bases. And what they said is a Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. All right. So now we're talking about just the protons moving around, and that's a much easier definition because we're not necessarily dissociating into a proton. We are accepting or making, right, or donating a proton is what it is, okay? So this is the common definition that when I talk about acids and bases, this is where we usually think about it, right? Whether protons are being donated or accepted, right? Now, when we put that into context of water, right, then we talk about hydronium and hydroxide and all this kind of stuff along the way too, right? But if we take our buddy ammonia, right, this is our proton acceptor, right? If we bubble it through water, right, this is our proton donor, and we can make ammonium and hydroxide, right? This is the stuff that you guys can just buy at the store, right? The ammonia cleaner, that kind of stuff. So all it does is the proton acceptor, right, takes an H plus away from H2O. And if you take a plus, right, an H plus away from here, you make OH, and you make an H4 plus here, that's all it is. Yeah?
So how exactly is that happening? Because typically, aren't the bonds that hold water together, like, relatively strong?
What bonds?
The,
You're talking about intermolecular or intramolecular?
intra.
Intramolecular. So intramolecular, yeah, like a hydrogen-oxygen bond is pretty strong, but what are you trading it for? A nitrogen-oxygen.
So since nitrogen is more electronegative?
No, it's not more electronegative. What my point is that, so maybe this might answer your question here in just a second, right? But there's a little bit of a, how do I want to say, a typo, a misnomer, something to pay attention to. If you'll notice, I've got this arrow pointing in one direction. Now that's not really true. Okay, what instead we establish here is an equilibrium. Okay? Wherein at some point, to some degree, to some percentage, to some ratio, to some K, right, we have these products over here, right? But remember, when we're talking about equilibrium, right, we have our forward and our reverse reactions going. Got it? So there's an equilibrium that's established wherein we have at some point in time hydroxide and our ammonium, right? And at other points we have our ammonia just dissolved into water, okay? And so this is what we're going to be spending our time figuring out. To what percentage, right? To what percentage does this exist, or to what percentage does this exist? Got it? Do you guys see where K is starting to fit into this? If I've got a large K, what does that mean? I'm product favored. If I have a small K, I am reactant favored, right? So that's all we're going to be doing. So we're doing exactly what we did, right, in the last chapter, except now we're just kind of just looking at acids and bases. Got it? That's it. Okay? Now, to bring in a little bit more definitions, I guess, we talk quite frequently about strong acids, strong bases, weak acids, and weak bases. Later on, I forget exactly, I know it's in there, I'll have a slide for you guys about what are the strong acids. And it'd be extremely useful for you guys to memorize those. Why? Well, practically, there's two reasons. One, if you guys recognize a strong acid, it's simply, how should I say this? It changes the math that we need to do to calculate Ks, okay? So if I ask you guys a question and it says, I give you one of the strong acids, there's a certain math that we can do with that that's different if it's a weak acid. Essentially, to put it simply, strong acids you don't always have to do an ice table with, is kind of what it is. Right, with weak acids we will, okay? And we'll talk about why that is and how, and we'll bring that in. Right, but just at the immediate point, right, for practical purposes, strong acids will have different math involved with them. The other reason is that we see strong acids used everywhere, okay? And so being able to recognize those and understand that they're strong acids help us to categorize what type of chemistry is happening, okay? And we'll give an example of that in just a little bit here. Weak acids, let me back up, right? So strong acids and bases completely ionized, right? I say almost there, and we're talking about 99.9%, right? So of course there's an equilibrium, but this equilibrium is heavily product favored, right? Heavily product favored. So we'll see almost no reverse reaction. We're talking about taking nitric acid, HNO3, right? That's nitric acid. It'd be very important for you guys to know the names and the formulas for these, all right? So when we take nitric acid and pour it into water, we dissociate completely into H3O plus and into NO3 minus, right? So now it'd be good also to start looking at that equation that I have up there and say, what's the acid and what's the base, right? What's the proton donor and what's the proton acceptor, right? And so I think we've got a couple examples coming up with that also. Yeah, what's up?
So does strength of acid under this definition also correlate with how corrosive they are?
Yeah, but I mean, we'd have to be careful, right? Because corrosive to what? To metals, to biological things, right? Plastics, that kind of stuff. Okay. Like HF, hydrofluoric acid, is not considered a strong acid, but it'll etch glass, it'll dissolve bones, right? So what do we mean by corrosive, right? It's an interesting question. Now, weak acids do not fully ionize, right? And so for those of you guys who are taking very close notes here, you'll see that for the strong acid, I just put the one arrow, right, indicating complete, right, quote, quote, complete ionization. Whereas with weak acids and bases, they don't completely ionize. And we establish an equilibrium, and once we establish equilibrium, guess what you guys have to do? K it up, right? Products over reactants, yada, yada, yada. Yeah?
Isn't HF considered a strong acid though?
No, technically no. Now your question might be, why, right? Yeah, so good question, and there's, let's say there's lots of good answers for that, right? For what our purposes are here, and in reality, I'm not lying to you guys on this one, right? HF isn't considered a strong acid. Is it a strong acid? Yes. Is it one of our 6 strong acids, though, that we're going to deal with? No, right? I'm not saying it isn't acidic. It is very acidic, but it's not a strong in the term strong that I'm using here. It doesn't completely ionize in water.
So all strong acids would completely ionize?
Correct, correct.
So another way we could look at this is we need to not think about the acid strength in terms of the pH scale and think solely for this in terms of how much they ionize?
Yes.
Is this essentially
That's
separate
fine,
from
yeah.
pH scale?
Hmm?
Is this essentially separate from pH scale?
No, of course it isn't separate, right? I mean, one's gonna affect the other, however, right, pH is a measure of concentration, right? Here we're just saying, does it dissolve, right? You know, even if I put 0.001 moles of nitric acid into water, it's still gonna fully dissociate. That doesn't mean it's gonna change the pH all that much, right? If I put 5 moles of HF into water, right, it doesn't dissociate, but it's probably gonna have a lower pH than the 0.001 moles of nitric acid. But that's a matter of concentration, right? Just to put numbers. I don't know if that's actually gonna be true. I assume it is, right? I think you get the idea here, right? So, right, the terms strong and weak are just referring to whether they dissociate or not, right? All right. Now, when we're dealing with equilibrium, remember we have reactions that go in both directions, okay? So we have our acid and base, and if we're going in the other direction, we have our acid and base there too, right? And so, we're gonna talk about conjugate acids and bases here in just a little bit, right? But remember, depending on which side you're starting on, which end you're looking at, right, we should be able to identify where the acids and the bases are. Now, first thing that you guys can do to kind of identify what the acids and bases are. So in the definition, right, in the definition of Bronsted acids and bases, right? So in the definition of Bronsted acids and bases, a Bronsted acid is what? A proton donor, right? Okay, what's a proton? Something that has a plus, right? It's a proton. So why do you think that we consider this to be an acid? Well, it's got a positive charge on it, right? You see what I'm saying with this? So if you're looking for proton donors, look for things that have H's and positive charges. Is that always going to be the case 100% of the time? No, right? But is that a good place to start? Yes. You guys with me on this? Hang on, right? Now, if you're a Bronsted base, okay, if you're a Bronsted base, what are you? You're a proton acceptor. Okay, what charge does a proton have? Proton has plus, and if I want to accept a proton, what should I have then? Probably a negative. Why? Because all of chemistry is what? Opposites attracting, right? Something negative attracting something positive, okay? So if we take a look over here, right, we have F minus, we have OH minus, both of those would be considered our bases, okay? Negatives and positives attract each other. You guys with me on this? Right, we're looking for pluses and minuses. That's going to be something important to start to pay attention to in this chapter. Really important. Okay, what is a plus? What is a minus? Where did it come from? What can it do? All these kind of things. Yeah.
So the bottom equation there, the NH plus and OH minus, aren't those both like pretty strong according to this definition? Like, wouldn't they just kind of cancel each other out?
I don't know what you mean by that. Could they react with each other? Is that what you're saying?
I guess, yeah.
Well, yeah, right? That's what an equilibrium is. This is going to go back to here, right?
So is it gonna be a lot more reactant favored then?
Good question. We'll figure that out. Right? We'll figure that out. What's up?
So based on the Bronsted definition, one substance in one equation could be an acid, but it could be a base in another?
Aha, yeah, that's a very interesting observation. Absolutely correct, right? In fact, there's a very common reaction that you guys will learn in organic chemistry, where we mix two strong acids together, nitric and sulfuric, right? And these are powerful acids, extremely powerful acids. But there's still a difference in the strength in between those two, and one's going to act as a base and the other's going to act as an acid, right? Even though, right, they're both in the strong definition that we have up there, right? So we do have to have some kind of, let's say, objective measure of strength. And we're going to talk about that in a little bit also, right? Give me the exact measure of strength for this acid. And then we can compare that number and say, because of this number, then I know this is the stronger acid, right? So good observation. All right, cool. So if we take all this stuff and kind of put it visually here, kind of what's happening, what's going on, right? If we have water and hydronium and chlorides and acetic acid and acetate, AKA, right, we've got a strong acid here, right, and we got a weak acid here, right? All we're saying is complete dissociation versus partial dissociation, right? There's things moving backwards and forwards, although here in the strong acid, they're going to stay, right, in the ionized form. That's all it is. Got it? Now, later on, and when you guys get to OChem and all these kind of things, we'll talk about the leveling effect and just what that means and kind of what implications it has and all these kind of things in there, right? So there's a lot more that we're kind of leaving off, and I'm happy to answer those questions, but just understand we're learning the basics at this point too, right? So anyway, right, visual representation of what's happening here, okay, what's going on within equilibrium. Okay, so water is going to be pretty darn important in this chapter, right? And in case you guys hadn't figured it out already up to this point, water is pretty darn important in pretty much any science. Right? So, but what I mean in this case is that understanding the role of water and how it fits into our calculations and how we can use information, right, to back out relevant numbers with the information that water gives us is going to be extremely important, right? So, AKA water is important for math. Okay. So water acts as a base when an acid dissolves into water, right? So it acts as a base. It's going to accept a proton, right, from the HBr, right? Hydrobromic acid is one of our other strong acids, right? So HBr is a strong acid. And if we mix those two together, we're going to make H3O plus and Br minus. Okay? Does everybody see, right? Can everybody start to write that equation there, right? HBr plus H2O makes H3O plus and Br minus, right? We have a transfer of a proton in between the two components, right? The acid loses an H plus, the base gains that H plus. Okay? Yep, what's up?
Isn't bromine one of our diatomics?
It is.
So why is it like sitting happy being a?
Oxygen is one of our diatomics, right? Mm-hmm. So take a deep breath. And then exhale. What are you exhaling? CO2, right? Why did it react with the carbon? Why isn't it sitting happy as O2? And just because it exists as a diatomic doesn't mean that it's not going to react with something else. Br2 would much rather be bound to an H than itself, right?
Okay.
So, for some bases, right, like ammonia, right, then water is going to act as an acid, right, and we generate that equilibrium that we're talking about, and then if we put the term with it, right, we just call it amphiprotic, right? It can donate or accept a proton. That's all it is. So in case you want to impress your friends or win at Scrabble, now you guys have a new word there to kind of put together, okay?
Okay, follow-up question.
Yep.
How is it a strong base if that Br would much rather be bound to a hydrogen? How's the water ground?
Because you're assuming that the hydrogen wouldn't rather be bound to the oxygen. It's not always about what you want, Rachel. It's about what others want. But it's a good question, right? And the question is, well, why in the world does any reaction happen to begin with, right? And we'll answer that in a couple of chapters. We'll talk about a little bit more about thermodynamics. We'll talk about entropy and free energy and all these kind of things, right? The simplified version is the strength of a bond is important, right? HBr doesn't really have all that strong a bond. It's much easier for oxygen to bond with the hydrogen than bromine is. Okay, so to bring in the terms that we've been talking about there, right? The idea of conjugate acids and conjugate bases, right? So when we're talking about conjugate acids and bases, we're just talking about how do things, what do they become once they react, right? So conjugate acid-base pairs, right? H3O, when it acts like an acid, its conjugate base is H2O, okay? When H2O acts as a base, it becomes a conjugate acid, H3O plus. You guys with me what I'm trying to show you guys here on this chart, right? When one side reacts as an acid, it becomes a conjugate base. When it reacts as a base, it becomes a conjugate acid. Good? So here's a couple more of our strong acids, sulfuric and hydrochloric acid for 2 more of our strong acids. Down here at the bottom, this is important too, right? We're talking about single proton steps, okay? Single proton steps. One hydrogen is gained or lost, and then another hydrogen is gained or lost. Okay, we won't be talking about 2 proton transfers simultaneously. One happens, and then the next, okay? But you guys kind of already knew this too, right? Because for 2 things to happen, right, that's not really an elementary reaction, right? So we'd have to have more than 2 things come together, which is kind of a big ask, right? Oh yeah, sorry, something else that's important on here. Take a note that, right, when we have sulfuric H2SO4, right, its conjugate base is HSO4, and then this can go on to react one more time there, right? And so this is one of these kind of quirks. I don't know, quirks, I should be careful. It's not really a quirk, it's a property, right? But when we have an acid that has 2 protons on it, H2SO4, sulfuric acid, H2SO4 is a strong acid. HSO4 has some different chemistry that we have to deal with there, right? And that's one of these fun questions that they like to ask in the book to make sure you guys are paying attention, aka trick you guys, right? So just be careful with it. And we'll talk a little bit about that as we get into the math, okay? Oh, apparently I already gave you guys the answers. Jeez, okay. Well, my question here is to identify the conjugate acid-base pairs. I think I forgot to take the answers out of there for whatever reason, but that's just fine, right? So, if we have HF and it's acting as an acid and it's reacting with hydrogen carbonate here, right? That's our base, right? We should be able to write our complete equation for this here too, right? So let's see if we can put this all together. So if we want to write this reaction here, right? So we have HF, aqueous, right? Plus HCO3, 1 minus. Right? So if we're trying to identify acids and bases, right? If I didn't give you the answers up here to begin with, right? Remember, what are we trying to look for here? Well, if we're looking for an acid or a base, we should start to take a look for what? Our charges that we have on there, right? So if I see something with a negative charge, right, the HCO3, and it's a good indication, right? It's probably a good bet that that's going to act as a base, right? Because again, what's the definition of a base? A proton acceptor, right? I want to accept things that are positive, so me, myself, I'm going to feel negative. Got it? And then HF is just one of those things where you guys will do so many examples with HF that you'll start to recognize it as an acid, even though it's not technically a strong acid, it's a weak acid. Okay? So if we put these together, right, then the HF turns into, right, the HF turns into F minus, right, and the HCO3 gains a proton, right, so, right, H2CO3, right, aqueous and aqueous. With me on this? Now, things to pay attention to. We have a negative charge on the left-hand side, we have a negative charge on the right-hand side. Make sure your charges all remain consistent. For those of you guys who are really, really paying attention, we say, how in the world can we just have a negative that's existing by itself? I just left off the sodium here is all it is, right? Spectator ions, that kind of stuff that we talked about in Chem 1, okay? So just paying attention to your charges and making sure they balance. If you start out with a -2 on the left-hand side, make sure you have a total of -2 on the right-hand side. Got it? So be careful about these kind of things. Cool. All right, so then a typical question would be identify the acids and bases. And so what I would want is for you guys to say this is the acid, right, and this is the conjugate base. Right, and then here we would say this is the base, and it forms our conjugate acid. Right? could go in the other direction also, where this is the base, and then that would be our conjugate acid, right? Especially when we're dealing with an equilibrium. Good. So this is just kind of a, I guess it's a little bit more focusing in on this idea here, but relating it to the strengths of the acids and the bases, okay? So we already know the stuff there on top, right? Strong acids are better proton donors, strong bases are better proton acceptors than their weak counterpoints. We got that. We understand what strong and weak mean, right? Stronger acids, though, this is extremely important. Stronger acids have weaker conjugate bases, okay? And weaker acids have stronger conjugate bases. This is extremely important, extremely important. The relationship between strength of an acid and its conjugate base, and strength of the base and its conjugate acid. This is another reason why identifying and knowing your strong acids is going to be important. Okay? Because if you know you have a strong acid, and now you know when it acts like an acid, it's going to make a weak base. Okay? Now, why is this the case? Well, we're going to ask some questions. They're going to say which side of the equilibrium is favored. Okay? And the quick way to answer that question is equilibrium favors the weaker acid. Okay? And we'll kind of contextualize that and give you my thoughts on that in just a little bit, right? But being able to identify the weaker acid on either side of the equation is going to be important. Okay? So here's our buddy's hydrochloric acid, one of our 6 strong, right? It's going to 100% ionize to make a very weak chloride conjugate base, okay? HF, not one of our 6 strong, right? So weak acid makes a stronger base, okay? That's all we're saying. Good? So identifying strong acids and bases, and then understanding their relationship to their conjugates, extremely important. So if we have an incomplete list here, and so I think in the back of your book, I forget exactly what appendix it is in, right? But they have this massive table of pKa's and Ka's and all this kind of stuff, which will be useful when you guys are working through the problems in this chapter, right? You're going to need to know that information, right? But, you know, if you just put that in the table form and, you know, rank the strength of acids and all these kind of things. Excuse me. So up at the top there, sulfuric, H2SO4, HBr, HCl, HNO3. Those are 4 of our 6. You guys can add HI, right? HI, hydroiodic HI. Okay, and then HClO. Let me write this legibly. HClO4, okay? Perchloric acid, perchloric. So HCl, HBr, HI are 3 hydrogen halides, hydrohalogens there. And then nitric, sulfuric, and perchloric. 6 things that'll make life that much easier for you, yes? Oh, yes. I did this with my other classes that I taught this stuff with. I told them, make sure you can recognize your 6 strong. And I asked them this extremely complex question on an exam, where if they had just recognized that it was a strong acid, they could have solved it in 30 seconds, right? Extremely important to recognize it. Now I told you guys that, now you're gonna be looking on the next exam for this, right? I'm not gonna ask that same question again. It ended up being a little bit too tricky. I didn't mean it to be that way, okay? I'm telling you, right? If you guys got the point, do I need to keep emphasizing it? Know the 6 strong, is that good? No, okay, I need to emphasize it more then, right? I see half-hearted nods all around. What's up?
Does it matter, like, should we memorize them in order?
No, you don't have to know the relative of those, right? Just be able to identify those as 6 for all, right? That's all.
And is HI above HO something?
No, it's, well, actually, let me think about this. I can't remember the pKa. I think it's below it relative. I'd have to look up the numbers to be honest, right? I don't have that stuff memorized. All I know is they're strong and what they behave with, right? I don't expect you guys to know those values either, right? I would give you that information. Okay, so something important here though, take a look at right below HNO3, nitric acid, HNO3, nitric acid. Right, you'll see what's right below it. H3O plus. So remember, H3O plus is this thing that we're going to see over and over and over and over and over again in this chapter. So what is that telling you? H3O plus is what? A pretty darn strong acid, okay? Pretty darn strong acid, okay? And then down here at the bottom, you'll see H2O. So what does that mean about H2O? It's a pretty weak acid, right? Pretty weak acid. So we'll put some numbers with that, right? Although you guys probably already know the strength of water and all these kind of things, right? How strong an acid or base it is, right? But we'll put some numbers with that. Okay, so do I expect you guys to memorize this chart? No. What do I expect you guys to know from the chart?
The 6 strong.
Thank you. Got it? Oops. Not what I want. Okay. So first of all, here's a typical question, right? Is the following aqueous reaction product or reactant favored, right? Product or reactant favored. See what you guys can come up with. See if you guys can. What would be good is to identify the acids on both sides and the bases on both sides, right? See if you guys can identify the acids and bases on both sides. And see if you can convince yourself why they are the acids and bases. Or better yet, convince your neighbor, right? Oops. Sorry, I should match the colors that are already on there, excuse me. So red is acids. Good? And the answers were on the board. I hope you guys got it. Who cares, right? Well, how do we answer this question? Let me walk you through my thought process with this, right? So if we ask the general question of which side of the equilibrium is favored, and I don't give you any numbers or any of these kind of things, right? Then the way to answer that question is saying, well, equilibrium favors the weaker acid. That means the side that has the weaker acid is going to be favored in the equilibrium. You guys with me on that? Now I get to ask my favorite question, which is what? Why? Right? Why? Why would equilibrium favor the weaker acid? Okay, let's start by answering another very important question. What does it mean to be a strong acid, or a stronger acid, I should say? A gooder acid, yeah.
It causes more ionization, it's doing more of the process,
What process?
the donation or acceptance of the
Be very specific. If you're an acid, you are
donating.
donating, okay?
So
So if you're an acid, right? If you're an acid, your purpose in life, right? The reason why you wake up in the morning is to donate a proton, okay? You guys catch what I'm saying with this? So if you're a gooder acid, right? How do you want to act?
generously.
Like an acid. You guys with me on this? And how do acids act? They act as proton donors. Okay, so now if I take away all the stupid sayings with this, right? If you're a stronger acid, you're going to behave like an acid. That's all I'm saying. And if you behave like an acid, you're going to react like an acid. And you're going to react more, okay, than your weaker counterpoint. That's all I'm saying with this. You guys following along with this very, very important idea, okay? Strong acids will act like acids. That's all I'm saying. So find the side that's weaker, because if you're weaker, guess what you won't act like? As much of an acid. You guys with me? And what did your parents always tell you? Don't make an acid of yourself. No, that's not what they said. What's up?
So you're saying stronger acids more readily donate a proton?
Exactly. Exactly. Right? So they're more likely to behave like an acid, they're more likely to react. And if they're more likely to react, that means they're going to make the products more frequently, right? So they're going to favor the other side. Yeah.
How come it's more dependent on strong bases, or strong acids and not strong
Great
bases?
question. Fantastic question. So, we'll get into that, right? We'll get into that a little bit more. But unfortunately, this is kind of related to a lot of the, not unfortunately, it's a fantastic question. It's related to some of the other questions that you guys have been asking all along. Why do these bonds form? Why do these things form to begin with? All this kind of stuff, right? So the short answer is some bonds are stronger than others, right?
Okay.
And we can measure that, we can put something in with that, but there's also more to it than that stuff also, right? Good? Everybody with me on this? Could everyone explain this to your roommate if they ask you the same question? Okay, if you're like, well, I hope my roommate doesn't ask me that. Right, you guys get the point I'm saying? You guys should feel comfortable answering this type of question, okay? I like these types of questions. Sorry, I had to clear my throat to make sure everyone heard me very clearly, okay? I like to ask questions like, can you explain your answer, okay? I don't need you guys to write me a treatise. I just need to say, well, you know, stronger acids will be more likely to react like acids. Therefore, they will make their products, and so the other side of the reaction is favored, right? We favor the weaker acid, that kind of thing there. Good? Something along those lines. All right. So I guess we should finish up this here, right? So, let's see, this looks like a good color, right? This looks like a good color, right? We see HF is a stronger acid, right, than NH4, right? So this is the weaker acid, so we'll favor this side of the equation over there, right? You guys with me on this? That's all it is. Okay? Now, do I expect you guys off the top of your head to know that HF is a stronger acid than that? Probably not, right? But, you know, if we call something hydrofluoric acid, it's probably a big hint. It's not our 6 strong, but it is a strong acid, right? Ammonium is it's not that good of an acid, right? All right. Cool. So now that we've talked about that stuff, let's start to bring some equations in with this. Okay. So if I ask you guys to write the equilibrium expression, right? If I ask you guys to write K for that reaction up there, right? two waters coming together to form H3O plus and OH minus, okay? You guys would do products over reactants, right? But notice our reactants are just water. Pure liquids are left out of our equilibrium expression. Got it? Right? So if we write a K for the autoionization of water, okay, then that'll be all that we have in there. Okay? Now, why do we care? Who cares about this kind of stuff? Well, if you take a look at the previous charts that we've had there in your book about the the relative strengths of acids and bases, you notice that water is on there both as an acid and as a base, right? That was one of the slides in our notes. Now, it's not a great acid and it's not a great base, okay? But to a certain degree, right, in your water bottles right now, there's a certain percentage of H3O plus. But there's also an equal percentage of OH minus. Got it? Right? Or, I should be careful. There's a pretty darn close percentage of the two, right? What's up?
So in the lab, we have deionized water.
Correct.
So what process has been done to get rid of?
Nothing. I'm not talking, deionized water just refers to, is there like sodium or potassium, any of these other types of ions in there. We can't stop this until you, take it out of the liquid phase, basically, is what it is, right? So, now, something important to note, the equilibrium is heavily reactant favored, okay? You guys already knew that too, right? Right. How did you guys know that it's reactant favored? Well, what's a stronger acid? H3O plus or H2O? H3O plus by far, right? And what did we just say in the previous slide? Your equilibrium is what? Favors the weaker acid, right? Now you guys know that because you're not chugging a bottle of ionized, completely ionized water too, right? You're drinking H2O. Just a small percentage of it is ionized, right? All right. Now this is going to be important, right? We're going to be able to use this to kind of back out some of the other important equations and get information about how much H3O plus and OH minus are present in certain solutions, okay? So we're going to see this KW come by quite a bit, and right, we just talked about this as the ionization constant for water, right? So we give it that term, it talks about that in the book. It's just another value of K. That's all it is. It's no different than the K's that we just got finished talking about, okay? All right, I'm sorry, you had a question, what's up?
So what is autoionization referring to specifically?
That it by itself can react to form the H3O plus with OH minus, right? It can do an acid-base reaction with itself, essentially. Yeah. But like with all equilibrium constants, that's the only thing that can change it is temperature, okay? So it is important to recognize what temperature we're dealing with, and we'll notice that as we change it, right, as we change our temperature, our KW will change too, right? Again, is this any different than any other equilibrium constant? No, it's not, right? Take a look at the values that we have here, right? Even if we're up at 50 degrees Celsius, it's 5.48 times 10 to the negative 14th. What does that mean to you guys? I gave you guys, or I'm giving you guys a value of K, right? Anytime you guys calculate K or you see it, right? One important thing to do is just, what does it mean? If I have something times 10 to the 14th, what does that mean? It's really, 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 really small value, right? Which means what? Heavily reactant favored, right? Times 10 to the 14th, there's nothing. There's practically none of that H3O plus there. Right? Well, why do we care about it then? Well, we'll talk about that, right? So what does this mean, right? Remember KW, right? This is equal to the concentration of this times the concentration of that, right? Which means that we can actually find the values for H3O plus and OH minus, the concentrations of those, okay? So the concentration of these are 1 to the negative 7th, 1 to the negative 7th, okay? Good? So if we take this idea, right, and start to kind of expand upon it a little bit, right? In a neutral solution, right, we have equal concentrations of our acids and bases, right? This is probably a term you guys are familiar with, right? A pH of 7 is considered a neutral solution, right? We have equal concentrations of hydronium and hydroxide, okay? If acid is added to water, right, we increase the concentration of H3O+, okay? So I know we're in the context of acid and base, but what are we doing here? We're adding something to one side of our equation. Got it? Okay? So we are disturbing our equilibrium. Okay? So our equilibrium shifts to remove, right? That side there, and our equilibrium is reestablished, right? And we happen to have more of our H3O+ than our OH-, right? Because that's just what happens with our equilibrium, right? We're talking about Le Chatelier's principle here. Okay? We're reestablishing equilibrium, but we do change the concentrations of those. Okay? All right. So we can go to the other direction, right? We're making something acidic here. And we can do the exact opposite here, right? If we add a base, the equilibrium shifts, right? And our new concentrations are such, right, that we have more hydroxide than hydronium in solution. Okay? But we're not changing temperature. And that's why I'm telling you guys there at the bottom, right? Kw, right, doesn't change unless we're changing temperature. Good? All right. So, calculate the hydronium and hydroxide ion concentrations at 25 degrees Celsius, okay, in a 6.0 molar aqueous sodium hydroxide solution. Okay, right? So what am I doing here? I got some water, and I added in sodium hydroxide, right, NaOH. Now NaOH is a base. How do you guys know it's a base? Because guess what it has in it? Hydroxide. Got it? Cool.
Hey, is there a functional difference between ionic and covalent bases?
A functional difference? Yeah, absolutely.
So,
right? At 25 degrees Celsius, Kw is equal to 1 times 10 to the negative 14. That is still a constant, right? Oops, wow, that's what we'll get to, but let's say that there, right? Right, that's what Kw is equal to. We need to figure out what these are, right? But we have our hydroxide concentration. It's 6, right? How do we know that it's 6? How do we know that it's 6? Let's think about this for a second, right? So, sodium hydroxide, NaOH. It's an ionic compound, right? We check our solubility rules. We remember that anything with sodium completely dissociates when you put it into water, yes? So what happens to NaOH? It completely dissociates when you put it into water. It completely dissociates into what? Na plus and OH minus. So if I have a 6 molar NaOH, guess how much OH I have? 6. You guys with me on this? Straightforward, right? It's something important to recognize and ask yourself the question, is this going to completely dissociate or not? If it doesn't completely dissociate, then we have to go do some different math. Okay? What's up?
I actually missed something here. Our K is in products over reactants in the last chapter.
So So what are you thinking about?
It's concentrations of our products multiplied by each other.
Mm-hmm. Right? So products over reactants, however, because they're pure liquids, right? Okay. Oops. So 1 times 10 to the negative 14th equals H3O plus, bad brackets, times 6, right? Good? Nice and easy. What do we get up with? Our hydronium concentration. I did my math and I got H3O plus equals 1.7 times 10 to the negative 15th. Yes? Right? Unless I did something wrong. Oh, negative 14, not negative 4. Good? That's all it is, right? So what does that mean? Wow! Times 10 to the negative 15th, holy crap! Okay, so let's think about this for just a second. So at a neutral pH, right? At a neutral pH, the concentrations of hydronium and hydroxide are equal, right? So what did I do, right? At a neutral pH, this is times 10 to the negative 7, and this is times 10 to the negative 7, right? Now it's what? Times 10 to the negative 15. So what happened to the concentration of this? It went down by quite a lot, right? By quite a lot. So we decrease our hydronium concentration. Now, I know you guys see this, I know you guys can recognize what numbers mean, but this is important because of what we're going to be talking about when we get to pH. Okay? Because pH is a measure of how much hydronium we have. If I decrease the amount of H3O plus, right, my pH goes up. Okay? So we're going to have to pay very close attention to what happens to the H3O plus concentration. Good? All right. So we will continue on with this on Wednesday.